Good morning, all of you. So, we have completed solid state up to lecture number 4. Now, next, we are going to do the last lecture of solid state, that is lecture number 5. So, here I am sharing the slides. So, few solved examples for the students preparing for competitive exams in solid state. This I feel it is most important. That's why I have added these slides also. And today we are going to end this chapter in this lecture. That is solid state, total 5 lectures. So this is the 5th lecture. Now come to few solved problems. So this topic will be for the entire chapter. So we are going to discuss all these questions. Now question number 1, you can see here. It can be seen now that both FCC, that is face-centered cubic lattice, and hexagonal primitive structures have the same packing fraction. That is hexagon. Already I told you, FCC, CCP, and hexagonal have the same packing fraction. That is, their packing fraction is 74% is occupation and 26% is void space. Moreover, this is also the highest packing fraction of all the possible unit cells with one type of atom with empty voids. Can you explain this? The solution is for this. So HCP is of the ABAB type. So we have seen in the diagrams in the lecture ABAB type, and FCC is ABC type. In HCP, FCC and in HCP and FCC both, the layers are formed of same atoms of the same type in the same arrangement. This is very important. The layers are formed of the same atoms, the same type, the same arrangement, each pair surrounded by 6. Each pair surrounded by 6. But the placement of the layers on top of each other is different. Both will have same packing fraction. So either you take FCC or HCP, they have the same packing fraction. And this is the highest packing fraction. This is the highest packing fraction possible because in both types, maximum number of atoms of the same size are present around the atom, namely 6. 6 atoms are present. Already we know in FCC also we have 6 atoms, and this HCP also 6 atoms, CCP also 6 atoms. So this is a question which is very important for discussion. That's why I have added this question, that HCP and FCC have highest packing fraction with one type of empty voids. Okay, next question. Now these models already we have done in the last session. Still some more questions have come. These are all previous NEET questions. So the radius of calcium ion is 94 picometer, and of an oxide ion is 146 picometers. That is calcium and oxygen. Predict the crystal structure of calcium oxide. Here in the previous section we have calculated only radius and edge length, but here they are asking what is the structure of calcium oxide based on the radius ratio. The radius ratio of calcium oxide, when this type of question arises, you have to see the radius ratio. And if you find the radius of cation to radius of anion, we have got it as 0.644. It means the prediction is an octahedral arrangement. That one table is given to you in the lecture 3, where you can see that table based on the values what type of arrangement. So this, since it is in the range of 0.644, the prediction is an octahedral arrangement of the oxide ions around the calcium. Because the ions have equal opposite charges, there must be also an octahedral arrangement of calcium oxide ions. Hence, it would be like rock salt structure, that is NaCl structure. So this is the answer for this, and this question is most important. So it has octahedral arrangement and undergoing similar to rock salt structure, that is NaCl. And I have explained clearly what is NaCl consisting of and what is the crystal lattice of NaCl in the lecture 4 and lecture 3. Next question. The unit of silver iodide has 4 iodine atoms in it. It has how many iodine atoms? 4 iodine atoms. And how many silver atoms must be there in the unit cell? This is also a very interesting question. The formula of silver iodide tells us that the ratio of silver atoms to the iodine atoms is 1:1. Hence, if there are 4 iodine atoms, automatically there are 4 silver atoms. So it is representing like NaCl type, where the ionic ratio is 1:1. So number of atoms per unit cell is 1:1. So answer is 4:4. That is, if 4 iodine ions are present, automatically 4 silver ions is present. So this question is clear for you. That is question number 3. Next question. Question number 4. The coordination number of the barium ions Ba plus 2 in barium fluoride is 8. What must be the coordination number of the fluoride ions? This structure represents AB2 type, that is fluoride structure. So AB2 type, here we mark a note AB2 type. So in AB2 type, how the atoms of A and how the atoms of B will be present and where they are exactly present and what is the coordination number, it is already discussed in the structures of ionic solids. So here if you see, since the coordination number of barium ions tells us that it is surrounded by 8 fluoride ions, 8 fluoride ions, that is 8 into minus 1 because the charge of fluorine is minus 1. So it is minus 8. In order to balance out 8 negative charges, we need 4 barium ions because already we know barium is in plus 2 state. And so it is 4 into plus 2, it is 8. Hence the coordination number of the fluoride ions must be 4. It means fluoride ions must be 4 means what? Here the coordination number for one fluorine atom, four barium ions are surrounding. One fluorine ion, 4 barium plus 2 ions are surrounding. You will find that coordination number and the charge on the ions always balance out to neutrality. So the coordination number of fluoride ions should be equal to 4. It is representing AB2 type and it is fluoride structure. So this we have discussed in already in the ionic structures of solids. Next question. A solid between A and B has the following arrangement of atoms. A atoms are arranged in CCP array. CCP means FCC, where A atoms occupy all the corners as well as face centers, and B atoms occupy all the octahedral voids and half the tetrahedral voids. Very interesting question. This is writing formula of compound. A atoms occupying all the FCC pattern and B atoms occupy all the octahedral voids and half the tetrahedral voids. What is the formula of the compound? So in closed packing, the solution you can see here. In closed packing, the number of octahedral voids is equal to the number of atoms per unit cell. This already we discussed in the last session. And the number of tetrahedral voids is twice the number of atoms. Twice is important here. So in FCC, octahedral voids is equal to Z, that is equal to 4. And tetrahedral voids is equal to 2 into Z, that is equal to 8. So now, since B is occupying one atom of B in tetrahedral voids and one atom of A in octahedral voids corresponding to each A, thus there will be 2 atoms of B corresponding to each A. Hence, the formula of the compound is AB2. This already directly also we can see. See here, A solid between A and B has the following arrangement of atoms. A atoms arranged in CCP. So A is equal to 4. Straight away I am writing here A is equal to 4 in our method of solving. B atoms occupy all the octahedral voids, means B is equal to 4 plus, since B is occupying not only octahedral voids but half the tetrahedral, that is B is equal to 4 plus 4, 8. 4 plus 4, because octahedral voids is equal to number of tetrahedral voids is 8, but it is half the tetrahedral voids. So B is equal to 4 plus 4, 8. So B is equal to 8. So A is equal to 4, B is equal to 8. By this you can write A4, B8. A4, B8 common factor if you take AB2. So answer is AB2. So this explanation is very, very simple. So this question is also important. So this is the question. Next question, question number 6. In corundum oxide, corundum, I hope you remember corundum is Al2O3, that is aluminum oxide, Al2O3. That is Al is plus 3 oxygen state and O minus 2 oxygen state. So aluminum is plus 3 and oxygen is minus 2. Are arranged in HCP array and the aluminum ions occupy 2/3 of octahedral voids. Here aluminum ions are occupying 2/3 of octahedral voids. What is the formula of corundum? Straight away by seeing corundum only you can write Al2O3. But based on mechanism, if you see in CCP or HCP packing, there is one octahedral void corresponding to each atom constituting the close packing. There is one octahedral void corresponding to each atom constituting the close packing. In corundum, only 2/3 of octahedral voids are occupied. It means corresponding to each other oxide ions, 2/3 aluminum ions are present. So the whole number of ratio of oxide and aluminum ion is in the ratio 3:2. Hence the formula is Al2O3. Al2O3. This we can solve in another method also. That is in corundum, oxide ions are arranged in HCP array and aluminum ions are occupying 2/3. If we take oxygen is equal to HCP, HCP means 4. Oxygen is equal to total 4. Because it is occupying HCP means like CCP. So that is all face centers as well as corners. So we can say it is oxygen is equal to 4. Now, if you see aluminum is occupying 2 by 3 of tetrahedral voids, octahedral voids. Aluminum is 2 by 3 of 4. 2 by 3 of 4. That is because number of octahedral voids is equal to Z. So 2 by 3 of 4, it is 8 by 3. It is 8 by 3. Oxygen is equal to 4. Aluminum is equal to 8 by 3. So by multiplying with suitable number, we got oxygen is equal to 12, aluminum is equal to 24. 8, sorry, aluminum is equal to 8. So by this we can say Al2O3 because 4 2 times, 4 3 times. So answer is Al2O3. In this way also we can find out. So this is the method of representing the formula of compound Al2O3. Next, question number 7. This table is very, very important. As I told you, this table decides by seeing the radius ratio of cations and anions, we can say whether it is what the shape of the crystal might be. Calculate the ratio of alkali metal bromide on the basis of data given below and predict the form of the crystal structure in each case. Ionic radii are given below, in picometers are given below. They have given ionic radius of lithium, sodium, potassium, rubidium, cesium, and bromine is given. So lithium bromide, sodium bromide, potassium bromide, rubidium bromide, and cesium bromide you are supposed to find out. So the ratio of cation to that of anion gives clue for crystal structure. So here the clue is for lithium ion and bromine, if you take the radius ratio, that is 74 by 195, it is coming around 0.3719, which is shows it is tetrahedral shape. So the ratio. And next, sodium ion to bromine ion, it is coming around 0.523, so it is octahedral. 0.414 to 0.723 is octahedral. So similarly, K plus Br minus, it is 0.708 we are getting, so it is octahedral. And similarly, more than 0.715, so that is for rubidium and bromine, it is coming around 148 by 195. It is coming around 0.75, and it is so it shows body centered. And cesium and bromine also body centered. So we have octahedral shape, tetrahedral shape, and body centered. So if the radius ratio is in the range of 0 to 0.225. 0 to 0.225. 0.225. It is simple cubic. You have to note down this clearly. Simple cubic, that is cube shape. If it is it is showing the range of 0.225 to 0.414. That is greater than 0.225 to 0.414. It is tetrahedral shape. And if the radius ratio in the range of 0.4 greater than 0.414 to 0.760, it is octahedral. And from 0.76 to 0.1, 0.76 to 1, 0.76 to 1, it is body centered. So this table is very, very important. These are the range values. So we have the shapes, crystal shape of the crystal, tetrahedral, octahedral, body centered, body centered. So since 0.759 has come, 0.759 has come, so it should be 0.75 only. Here it is only 0.75. So since 0.759 has come, it is body centered. 0.75 to 1, it is body centered. Approximate values have given. So this radius ratio, by seeing the radius ratio, we can see the shape of the crystal. So structure of crystal, that is not shape, structure of the crystal. So this is clear for you. Based on radius ratio, we can find the structure of the crystal. This model is most important. That's why I have given here. Next. Next, in the closed pack cation, in an AB type solid have a radius 75 picometers. What would be the maximum and minimum size of the anions filling the voids? Very, very important model. Here, they have given the closed pack cation in AB type solid have a radius of 75 picometers. What would be the maximum and minimum size of the anions? So, For close packed AB type solids, the radius ratio, as I told in the previous question, R plus R minus is in the value of 0.414 to 0.7342. Approximately, I have told here in the previous question, 0.75. This is the correct value, 0.414 to 0.7342. So minimum value of R minus will be R plus by 0.732, because maximum you have to take. That should be 102.5 picometers, and the maximum value of R minus becomes R plus by 0.414, because if we take the lower limit, we'll get maximum value. If we take the higher limit, we'll get the minimum value. So by taking maximum value, minimum value of R minus is nothing but R plus by 0.732, and it is coming around 102.5 picometers. So the maximum minimum size of the anions filling the void should be, the minimum value of anion is 102.5 picometers, and the maximum value of anion will be 181.2 picometers for this type of solid. Hence, the table is very, very important, where we can find maximum minimum filling size of anions as well as cations. If they ask for cations also, we can take the values of anions and we can find the ratio of the cation, so on. Next question, question number 9. NH4Cl, that is ammonium chloride, crystallizes in a body-centered cubic lattice with a unit cell distance of 387 picometers. So 387 picometers. Calculate the distance between the oppositely charged ions in the lattice. Very, very important new model we have got. Distance between the oppositely charged ions in the lattice, and also the radius of ammonium ion if the radius of chlorine ion is 181 picometers. Now, finding the solution. So, how to calculate distance between the oppositely charged ions? So, that is nothing but, in a body-centered cubic lattice, oppositely charged ions touch each other along the cross diagonal of the cube. This you underline, cross diagonal of the cube. So they'll touch each other at the cross diagonal of the cube. This we got it from the experimental study. Hence we can write 2r plus 2r minus gives us root 3 by a, root 3a. So r plus r minus is equal to root 3 by 3a by 2. So this is radius ratio, and that is equal to root 3 by 2 into 387 picometers, that's 335.15 picometers. Now since r is equal to 181 picometers, we have r plus is equal to 335.5 minus 181. So it is equal to 154.15. So this also we can take like this. For BCC, the distance between radius and edge length relation, r is equal to, small r is equal to root 3 by 4 a. And if you are taking radius of cation and radius of anion, so r plus and r minus is equal to r plus r minus is equal to root 3a by 2. Simply we have to divide it by 2. So applying this formula, we got r plus and r minus. And as we got total of r plus and r minus, that is equal to 335.15 picometers. Straight away, we can find, and r minus is given in the question, that is 181 picometers. So we can find r plus, that is the radius of cation, which is equal to 154.15 picometers. And one more important, already you know this, always radius of cation is smaller than radius of anion. So radius of cation should be smaller than radius of anion. Suppose if the same question comes in the examination and they are given 4 options, and the options in which we have seen that r minus is given 181 picometers. Luckily, if they are given r plus value as less than 181 and remaining 3 options is greater than 181, without solving also, straight away we can write r plus is less than r minus. So that option we can choose. But usually you will not find that type of options. They will give definitely all lesser than r minus options only. So it's better to solve the question. And for BCC, r is equal to root 3 by 4a, r plus r minus, that is sum of cations and anions, is equal to root 3 by 2a. So whatever radius and whatever the relation in any lattice between radius and edge length, already we have given the relation between radius and edge length for all the lattices. For BCC, r is equal to root 3 by 4a. For FCC, r is equal to a by 2. So to find the simplest distance, we have to divide it by 2. We find the simplest distance, we have divided by 2. So for in this case, it is BCC is given. So r is equal to root 3 by 4a. Root 3 by 4a. So for simplest ratio between the distance between the opposite charged ions, we have to do divide by 2. So we got the answer root 3a by 2. I hope this question you understood. I'm proceeding to next question. Copper has FCC crystal, assuming an atomic radius of 130 picometers for copper atom, and copper mass is also given, that is 63.54. You can take it as 63.5 also, it's not a problem. Now, first question, they are given only atomic radius, that is edge length of copper, that is 130 picometers, and from that they are asking what is the length of unit cell copper, and they are given the idea copper has FCC crystal. First question, what is the length of unit cell of copper? Second question, what is the volume of the unit cell? Third question, how many atoms belong to the unit cell? And fourth question, find the density of copper. This entire concept is given here in this one problem, very beautifully framed. That's why I want to discuss this problem. So first, to find length of the unit cell of copper, as we know, rho is equal to Z into M by A cube into Na. That is, N is called number of atoms per unit cell, and I told you know already, N and Z both are similar, and M is called molar mass, that is molar mass of copper 63.5, and N of A is Avogadro number, and which is equal to 6.023 10 to the power of 23. And A is called edge length. Edge length is given 130 picometers. Now for FCC structure, since already we know for FCC structure, the relation between here also from relation of radius, the relation between for FCC, the relation between radius and edge length R is equal to A by 2 implies, for this they are given 4R is equal to root 2A, that is by solving. So A is equal to 2 by root 2R. So A by 2 to R, simply we can say by substituting that value. Since A is given, we can find R, that is length of the unit cell. So that is A by 2. A is given here 130 by 2 into root 2. So you'll get the answer 130 by 2 straight away. We can find it out, and we got 367.64 picometers. And volume of unit cell. So volume should be measured in centimeter cube. Already we know 1 picometer is equal to 10 to the power of minus 10 centimeters. So we can say volume of unit cell is equal to A cube, that is 367.64. A is given here. They have given R. We have to find A. So A is given here 367.64 in 10 to the power of minus 10 centimeter cube. That is equal to 4.968 in 10 to the power of minus 23 centimeter cube. So this is the volume of unit cell. And already you know how many atoms belong to the unit cell. Since it is FCC, N is equal to 4, and P is equal to 4 into 63.4, that is rho, that is 4 into molecular mass. Molecular mass of copper is given by Avogadro number into A cube. So they have given here, they have given only R, and from that R we have to find A. So assuming atomic radius is given, I have taken it as length, it is not correct. Atomic radius is given. So from this case, A we have to find. So A is equal to 2 to R. A is equal to 2 to R. Root 2 A is equal to 4R. This expression you have to cancel it. This we have not done. We have to see A is equal to 4R by root 2. A is equal to 4R by root 2. So this, if you cancel it, you'll get R by 2 root 2. So answer will be 367.64 picometers, because they are given atomic radius. From atomic radius, we have to find edge length, that is length of the unit cell. And second one, volume of the unit cell. Volume of the unit cell will be A cube. For any unit cell, volume becomes A cube. And how many atoms belong to the unit cell, that is number of atoms per the unit cell, that is Z is equal to 4 or N is equal to 4. And density of copper by substituting the expression rho is equal to Z into M by A cube into Na, we got 8.54 grams per centimeter cube. So this is the entire picture of a question based on density of crystal and finding radius ratio, etc., etc. So this question number 10 is most important. I hope you understood it clearly. Next question, question number 11. The density of calcium oxide is 3.35 grams per centimeter cube. The oxide crystallizes in one of the cubic systems with an edge length of 4.80 angstroms. How many calcium ions and how many oxygen ions belong to each unit cell, and which type of cubic system is present? So Here the density of calcium oxide is given 3.35 grams per centimeter cube. So rho is given, and the oxide crystallizes in one of the cubic system. That it can be simple, it can be cubic, it can be FCC, it can be BCC. That also we have to identify. And edge length is also given 4.80 angstroms. How many calcium ions and oxide ions belong to each unit cell, and which type of cubic system is present. So from this equation we can say they have given radius, that is density rho is given. It is not R, it is rho. You can see here it is not R, it is wrongly printed, it is rho. That's why I have mentioned in the diagram. That is density. Rho is given 3.35. A is given 4.80 angstroms. Molecular mass of calcium oxide, already we know. Calcium is 40, oxygen is 16, so it is 56 grams of calcium oxide. And QR, that is number of molecules per unit cell, is equal to, we have to find that only first. If you know that number of atoms per unit cell, straight away you can decide the structure of crystal. So here everything is given except n value. So to find n is equal to 3.35 into 4.8 10 to the power of minus 8 whole cube, because 1 angstrom is equal to 10 to the power of minus 8 centimeters, and A is given 4.8 angstroms. So A cube becomes 4.8 in 10 to the power of minus 8 whole cube, and Avogadro number is 6.023 10 to the power of 23 by total 56. So this we got it as 3.98. It is almost approximately equal to 4. Since n is equal to 4, definitely this should be HCP or CCP or FCC. So 4 molecules of calcium oxide are present in one unit cell. So number of calcium ions should be equal to 4, and number of oxygen ions is equal to 4. So cubic system is FCC type. So in this way you can find out the question clearly. I hope you understood this. It is very clear. Here the density is given and edge length is given. From these two we have to find molar mass is also given. From these three we have to find only Z value, that is N value, that is number of atoms per unit cell. Once you got number of atoms per unit cell, we can decide the crystal of the structure. And since N is equal to 4, we got in this numerical, it is HCP or CCP or FCC type. Where if N is equal to 2, it is simple body centered. If N is equal to 1, it is simple cubic, and so on. So already these things we know. So this is the question number 11. I hope you understood it clearly. Question number 11 is finished. Next question number 12. So question number 12. These are all the different models which I have seen from all the entrance exams. That's why I thought this is important for you to discuss with this. So that's why I have given all these problems. And previously we have done lecture number 4 also, questions based on this topic only. But those questions are different from these questions. So that's why I have prepared the total concept into JEE mains, NEET and advanced level. So a student can comfortably understand all these videos, and he can do it, the numericals on solid state easily. A metal crystallizes in two cubic systems, face-centered cubic and body-centered. Here the same metal is crystallizing in two cubic systems. One is face-centered, another is body-centered, whose unit cell lengths are 3.5 and 3 angstroms respectively. Calculate the ratio of densities of FCC and BCC. Here you can see face-centered unit cell length is 3.5 angstroms, unit cell length, and BCC unit cell length is 3 angstroms. So density is equal to, already we know in FCC, N into atomic weight into V1 into Avogadro number, N2 into atomic weight into V2 by V2 into Avogadro number. That is volume 1, volume 2 density. So density of FCC by density of BCC is equal to N1 by N2 into V2 by V1. So N1 for FCC, already we know it is 4. And also V1 is equal to A cube, that is 3.5 10 to the power of minus 8 whole cube. And N2 for BCC is 2. Also V2 is equal to A cube, that is 3 into 10 to the power of minus 8 whole cube. So answer is 12.49. By solving this, we got the answer 1.259. 1.259 is answer. And this is called a metal crystallized in two cubic systems, face-centered and body-centered, whose unit cell length are given. Calculate the ratio of densities of FCC and BCC. Density is equal to mass by volume. So based on that mass and volume we have done. So atomic weight of A and atomic weight of B, and V1 by V2 Avogadro, because same metal, atomic weight gets cancelled. Avogadro number gets cancelled. So N1 by N2 into V2 by V1. By solving N1 by N2 into V2 by V1, N1 is equal to 4, N2 is equal to 2, we already know, and V1 is equal to A cube, that is 3.5 into 10 to the power of minus 8 whole cube, and V2 is equal to A cube, that is 3 into 10 to the power of minus 8 whole cube. So by solving this, we got the answer 1.259. So the ratio of densities of FCC and BCC for the same with the edge length 3.53 angstroms respectively is 1.259. Next, question number 13. Copper crystal has a face-centered cubic structure. Atomic radius of copper atom is 128 picometers. So here also they have given only a radius. Then what is the density of copper atom? Atomic mass of copper is given. So from basically by seeing this question, we can say if they have given edge length straight away, we can apply the formula rho is equal to Z into M by A cube into Na. But they have given here only atomic radius. First, we need to find radius. From atomic radius, we have to find edge length. So in face-centered cubic arrangement, face diagonal is 4 times the radius of atomic face diagonal. That is 4 into 128, that is 512 picometers. And face diagonal is equal to root 2 into edge length. Edge length is equal to 512 root 2. And it is also equal to like this. Instead of this, we can solve the same question as we can solve this question for FCC arrangement. R is equal to for FCC arrangement, R is equal to A by 2 2. The relation between radius and edge length is R is equal to A by 2 2. Since R is given from this, you can find comfortably A value. After finding A value, we can use this formula. Rho is equal to Z into M by A cube into Na. So this will be clear. So I'm playing the drawing also. So you can solve like this also. So in a face-centered cubic cell, mass of unit cell is equal to 4 into 63.5, 4 into 63.5 by 6.023 in 10 to the power of 23 grams, which is equal to 4.22 in 10 to the power of minus 22 grams. Density is equal to mass of unit cell by volume of unit cell. So finally, you'll get the value 8.9 grams per centimeter cube. So in this case, we can have two steps. One is directly instead of using this 4 into 128, 512 picometers, etc., straight away we can write R is equal to A by 2, 2, which I have written previously. So from that you can find, as radius is given, you can find comfortably edge length. Once edge length is given, you can find the formula density rho is equal to Z into M by A cube into Na. And Z value already you know, that is 4. And M value you know 63.5. A value you know Avogadro number 6.023 10 to the power 23. And Na. So that A value also will get the answer from radius of this thing. So you'll get the answer. I hope this is clear. So this is question number 13 is over. Next question. Question number 13 is over. Next, we have question number 16. What is the difference in the semiconductors? So this is different topic based on semiconductors. What is the difference in semiconductors obtained by doping silicon with aluminum or with P? So phosphorus. Here P represents phosphorus. So silicon doped with aluminum produces p-type semiconductor because addition of 13th group element, doping of 13th group element into silicon or germanium semiconductors, it forms p-type semiconductor because one electron is less. So because the charge of silicon is +4 and aluminum is +3, so the electron is responsible, that is flow is due to certain creation of positive holes, whereas silicon doped with P, phosphorus is +5 valency, produces n-type. So when you get p-type semiconductor, if, just note down this, very, very important, all the students, please note down. If silicon or germanium semiconductors are doped with 13th group element, that is aluminum, boron, etc., indium, thallium, etc., if it is doped with 13th group elements, we can say it is forming p-type semiconductor. 13th group element is important, p-type semiconductor, and flow is due to creation of positive holes. Whereas silicon, if silicon is doped with 15th group element, that is phosphorus, 15th group element, phosphorus, produces n-type semiconductor because due to extra electron. Because phosphorus valence is +5 and silicon is 4. So 4 and 5. So one electron will be extra. So due to this extra electron only, it carries negative charge. Hence they form n-type. N-type is negative and p-type is positive. So P type, how we are getting? If a silicon or germanium, that is silicon or germanium semiconductors are doped with 13th group element. 13th group element is positive charge is +3. So it requires one more electron to get balanced, because silicon valence is 4, aluminum valence is 3. So more one electron. So deficiency of electron, that is it carries positive charge due to creation of positive holes. Whereas silicon doped with phosphorus, that is 15th group element, that is called N-type semiconductors. I hope it is clear. So what is a P-type semiconductor? A P-type semiconductor is that in which a silicon or germanium is doped with 13th group element. 13th group element means not only aluminum, it can be any element of 13th group, that is boron, aluminum, indium, thallium. And if the silicon or germanium semiconductor is doped with 15th group element, that is phosphorus 15th group element, we can say it is called N-type semiconductors. So N-type semiconductors and P-type semiconductors. And the N-type semiconductor shows negative charge, carrying negative charge because of extra electron, and P-type semiconductor is positive charge because of deficiency of electron and more amount of protons. This is question number 16. I hope it is clear. Now question number 17. Non-stoichiometric cuprous oxide, Cu2O, can be prepared in the laboratory. In this oxide, copper to oxygen ratio is slightly less than 2:1. Can you account of the fact that this substance is P-type semiconductor? See here again giving clear option. Non-stoichiometric cuprous oxide, Cu2O, can be prepared in the laboratory. In this oxide, copper to oxygen ratio is slightly less than 2:1. Can you account for the fact that this is a P-type semiconductor? The ratio less than 2:1 in Cooper show that some Cooper ions have been replaced by cupric ions. Cooper ion Cu plus has been replaced by Cu plus 2 ions. Very, very important. So to maintain electrical neutrality, every 2 copper ions plus 1 ions will be replaced by 1 Cu plus 2 ion. This is only metal deficiency defect, and thereby creating a hole. As conduction will be due to the presence of these positive holes, hence it is a P-type semiconductor. So this is the explanation. I hope it is clear. So due to the creation of hole, it forms P-type semiconductor. P-type semiconductor means positive and N-type semiconductor means negative. And now question number 19. If NaCl is doped with 10 to the power of minus 3, this is very, very important question. If NaCl is doped with 10 to the power of minus 3 mole percent SrCl2, what is the concentration of cation vacancies? So here also based on doping. So for sodium chloride crystals, if you dope with 10 to the power of minus 3 mole percent SrCl2, that is strontium chloride, what is the concentration of cation vacancies? Doping of NaCl with 10 to the power of minus 3 per mole percent of SrCl2 means that 100 moles of NaCl are doped with 10 to the power of minus 3 moles of SrCl2. So for 1 mole of NaCl is doped with SrCl2, then it becomes 10 to the power of minus 3 by 100, which is equal to 10 to the power of minus 5 moles. As each strontium ion creates one cation vacancy, therefore, the concentration of cation vacancies becomes 10 to the power of minus 4 minus 5 divided by mole of NaCl. So 1 mole of NaCl contains 6.023 10 to the power of 23 units of NaCl. So answer becomes 10 to the power of minus 5 divided by 6.023 10 to the power of 23, which is equal to 6.023 10 to the power of 18 moles. This model is most important. If they are given 10 to the power minus 3 mole percent of SrCl2, it means for 100 moles, it is 10 to the power of minus 3. Suppose if they are given 10 to the power of minus 5, it means for 100 moles, it is 10 to the power of minus 5. So for 1 mole, 10 to the power of minus 5 by 100, it becomes 10 to the power of minus 7. And to find concentration of cation vacancies, we can say that the 10 to the power of minus 7 by Avogadro number. In this case here, 10 to the power of minus 5. So just giving an example. So like these questions are very, very important and very simple to understand. I hope this is clear for you. Now we are discussing the question number 20. In lithium iodide crystal, iodine ions form a cubical closest packing arrangement, that is FCC. So it is iodine ion forming FCC. CCP or FCC, and lithium ions occupy octahedral holes. What is the relationship between the edge length of the unit cells and the radius of iodine ion? Simple, it is calculate the limiting ionic area of lithium plus and iodine minus if A is equal to 600 picometers. Now from the question we can say 2R plus 2R minus is equal to 600 picometers because they are given limiting inequality. And from this we can say R plus by R minus, that is sum of radius of cation plus anion is equal to 300 picometers. Since lithium ion is octahedral holes, for octahedral holes the radius ratio is 0.414. This already we have seen in the table. And from equation 1 we can say R minus into R plus by R minus plus 1 is equal to 300. And by this iodine minus into 0.414 plus 1 is equal to iodine minus is equal to 300. So by this we can say radius of iodide ion, that is equal to 212.164. That is, since R plus by R minus is equal to 0.414. By this we can say R plus is equal to 212.164 into 0.414, which is equal to 87.84 picometers. So this is very, very important, and I hope this you can understand. Next, so these are the different types of questions which I thought it is important to discuss. So next, we have successfully completed this chapter. Now I'm writing the summary of the chapter. Please note down all these points and act accordingly what I said, so that easily you can answer any type of questions in any objective books or competitive exams. Any objective book you can solve. So summary of the topics. In the first session, we have done summary of the topic, summary of the solid state. First one, we have done about types of solids. In types of solids, differences between crystalline and amorphous solids table is very important for objective point of view. Please follow these differences between crystalline and amorphous solids. That is, crystalline is anisotropic and amorphous is isotropic, like that. So all the properties, difference between crystalline and amorphous solids table is important. This we have given in table clearly, so that that is important for objective point of view. Second model, types of solids. Second topic is types of solids. Table with examples and force of attraction. Table with example. Types of solids like covalent solids, molecular solids, ionic solids, etc. So types of solids also we have made a table with examples is given what type of force is acting between them. That is van der Waals force, hydrogen bonding, and so on. Next, topic 3 in this chapter. What this, if you do, you can answer any type of question from solid state for all competitive exams. That's why I'm giving you, making it first summary for you. Next, third type, we have to see about crystals, crystal lattice. Crystal lattice. In crystal lattice, we have to take care of this. First one, radius of cation to radius of anion ratios. Second one, density of crystals. Third one, writing formula of compound. Writing formula of compound. And fourth one, we have writing formula of compound. And fourth one, we have radius ratio, density of crystals, writing formula of compound. And we have voids and spaces. That is packing fraction. Packing fraction. Packing fraction of solids. So all these 4 points very, very important in crystal lattice. So definitely you'll get question from these 3 areas. And next, fourth important area we have done already, that is structures of ionic solids. Structures of ionic solids also is most important. We have done all the types of structures. So for example, structures of ionic solids like NaCl type, AB type, AB2 type, etc. And fluoride type, Woodside type structure, spiro compounds, spinal structure. All these structures have been given in the table clearly. So structures of solids, ionic solids. And fifth topic, we have defects in solids. Defects in solids is also very important that we have done. That is Schottky defect, Frenkel defect. In the examination, what they'll ask the question. So, and sixth topic, last we have electrical and magnetic properties of solids. Electric properties and magnetic properties of solid. Electric and magnetic properties of solids. So these are the 6 topics we have in solid state. 6 topics we have. All the 6 topics we have completed successfully in 5 lectures. And all the 6 topics, what type of questions we are going to get in the competitive exam, that also we have discussed. I hope it is very much clear for you. And properties of solids and electric properties of solids and magnetic. In magnetic fields, magnetic properties of solids, they'll ask about paramagnetism, diamagnetism, alignment of solids in ferromagnetic, and so on. So magnetic properties, they'll ask questions based on that only. Electrical properties, they'll ask about p-type semiconductor, n-type semiconductor. That question also we have discussed. And defect in solid, what is Schottky defect, what is Frenkel defect, and metal excess, metal deficient defect, and what are the consequences of defects also we have discussed. And structures of solids, definitely they'll ask cations occupy what, and anions occupy the position of, and coordination numbers. In structures of solids, you will get 2 types of questions, that is asking coordination numbers and positions of cations and anions. Positions of cations and anions, where the anion is placed, where the cation is placed. So in every structure, we have seen cations are placed in some voids, lattices, etc. So that is most important. And most important, definitely you'll get a question from third point, that is crystal lattice. Crystal lattice numericals are most important. I hope this we have done most, because we have done almost 30 to 35 problems. And by using these models, we can solve any questions. You can solve all the questions in any objective book for competitive exam. So whatever objective book you prefer, like gender material or any other material. So that is third area is most important. And to my knowledge, third area is most important for all competitive exams, third and fourth and fifth. If you do all the 6 models, entire solid state will be covered. So it's better to do all the 6 models for all the students, so that you should not miss that question in solid state. So all the 6 topics, if you do 100%, you can able to solve solid state in any competitive exam. And most importantly, in all the competitive exam, definitely that is either NEET or JEE Mains or JEE Advanced, they'll give one question, or BITSAT or any other engineering exams or medical exam. They'll give definitely one question from solid state. I hope this solid state is clear for you. This all the 5 lectures, if you listen carefully one time or more than one time, you can understand easily. I hope it is clear for you. Thank you all. And I'm ending this session of solid state. Next, we'll see in the next question.